Okay, welcome to your first video lecture in section 10.5 on separation of variables, heat conduction in a rod. The basic partial differential equations that we'll study in this chapter of heat conduction, wave propagation, and potential theory are associated with three distinct types of physical phenomena: diffusive processes, oscillatory processes, and time-independent or steady processes. In math, we call the first type parabolic, the second type hyperbolic, and the third type elliptic. These partial differential equations are of fundamental importance in many branches of physics, and the partial differential equations whose theory is best developed and whose applications are most significant are linear equations of second order, which is what we'll study in this chapter. Okay. So in this lecture we'll consider the heat conduction problem for a straight bar of uniform cross-section and homogeneous material. We'll allow the x-axis to be chosen to lie along the axis of the bar, and let the ends be denoted with x is equal to 0 and x is equal to L. We will suppose that the bar is perfectly insulated so that no heat passes through the sides, and that the bar is held at a constant temperature T1 at the left end point and T2 at the right end point. We will finally assume that the cross-sectional dimensions are so small that the temperature can be considered constant at any given cross-section of the bar. So what we're going to consider is just the temperature of the bar as a function of one axial coordinate x and time t. Okay, so the picture here is going to be of a bar, okay, all right, with the x-axis going through, the left end point being x is equal to 0, and the right end point being x is equal to L. And we're going to assume that heat is constant in every direction but left to right. So we're going to denote the temperature at that particular point to be U of x at time t. Alright, so that's what we're going to be studying in this section. Okay, here we derive the heat equation with a conservation law. We call h of t the total heat in an arbitrary interval, x, comma, x plus delta x, inside the interval 0 to L at time t. U of xt is the temperature at the spatial coordinate x and time t, and so the total heat is the integral from x to x plus delta x of the temperature times the specific heat and density of the rod. Okay, so that's the heat at time t. We will assume that no heat enters or leaves the rod via forces, and thus the only way in which heat inside the rod changes is through the flux term J of xt at each point xt. The rate of change in the rod's heat within the interval x, comma, x plus delta x at time t is equal to the heat flowing in at x minus the heat flowing out at x plus delta x. In other words, dH dt, which if we pull the differentiation under the integral symbol is going to give us the partial of u with respect to t times c times rho, is equal to the flux at x minus the flux at x plus delta x of heat. And so Fourier's law tells us that heat flows from hot to cold regions at a rate kappa greater than 0 proportional to the temperature gradient. In other words, we're going to assume that our flux is equal to the temperature gradient, which in the one-dimensional case is just the partial derivative with respect to x, times negative kappa. And that denotes the idea that heat flows from hot regions to cold regions. Okay, so if we use this as our flux term, we again get the rate of change in heat is now equal to negative kappa times the first partial of u with respect to x at x, and then plus kappa times the first partial of u with respect to x at x plus delta x. This is the outcome of the fundamental theorem of calc. The first partial with respect to u of x is the antiderivative of the second partial of u with respect to x. Okay, and so we put that into another integral symbol here. Okay, again with the integral going from x to x plus delta x, we combine the two integrals. we end up with this integral equation. Okay, since the interval we chose was arbitrary, the integrand must be 0, and thus we have this partial differential equation, which, if we do some reduction, we end up with this partial differential equation, which is the heat equation. Alpha squared is kappa divided by rho c, and it's called a diffusion coefficient. Example values for the diffusion coefficient are basically 1 3/4 for silver, 1.14 for copper, and a very small number for water. This partial differential equation has one derivative in time, two derivatives in space. So we need one initial condition. The initial condition is going to be a function of x, which we call the initial heat profile. We'll call that f of x. We can assume without loss of generality that the sides have temperature fixed at 0. You can show that going from the case where the sides aren't equal to 0 to the case where sides are equal to 0 is a simple transformation of the corresponding solution. So what we have then is this initial boundary value partial differential equation. The partial of u with respect to t is equal to alpha squared times the second partial of u with respect to x. Initially, the heat profile is f of x, and at the boundaries, the solution is equal to 0. Okay, thank you.